Welcome back. This is Principles of Physics, and we are in the middle of Chapter 16. So far we've covered static electricity. That's electric charge. Electric charge comes in two forms, positive and negative, so we know that. We know like charges are going to repel and opposites are going to attract. And we know charge is conserved, so we don't have a change in the net charge. If you get extra electrons over here, you'll get extra protons, or a deficit of electrons, because electrons are what move, a deficit of electrons over here. So we have conservation of charge. We know that electric charge, we can understand it in terms of understanding atom and atomic particles. So you can have a neutral atom with an equal number of protons in the nucleus and electrons orbiting it, or you can remove electrons. When you remove electrons, you end up with more positive charge in your atom, and that will give you a positively charged ion. Or you can add more electrons, that'll give you a negatively charged ion. We also talked about insulators and conductors. In insulators, charges don't flow freely. In conductors, electrons move very freely from one atom to another. Okay, and finally we talked about induced charge, both by conduction and induction, and we talked about how an electroscope works in order to figure out the charge of something. All right, so now we move on to Coulomb's law, which is the quantitative crux of Chapter 16. That's really the meat of this chapter. And then solving problems involving Coulomb's law. That will be the topic I cover in this video, and then we'll have one more video to talk about electric field, field lines, and field lines related to conductors. Okay, so Coulomb's law. Coulomb's law is a law given to an observation, and the observation was that experiments were done that showed that the electric force between two charges is proportional to the product of the amount of charge and inversely proportional to the distance between them. So that's putting Coulomb's law into words. So if you bring, say, a charged object near another charged object, and these are both positive, so they're like, so they repel, the force of repulsion is going to be proportional to the amount of the charge on each object. So that's, say, object 1 and object 2. The product of those, multiply them together, and divide by the distance between them. And that inversely proportional to that. And that gives us a quantitative way of stating Coulomb's law. Okay, quantitatively, we can put this into an equation form. So the force, so Coulomb's law gives us the magnitude of the force that one charged object exerts on another. Or you could say that charged objects exert on each other, which I can explain again in a second. So the magnitude of the force F is equal to K. That's a proportionality constant. We started out in the previous slide saying that it was proportional to the product of the charges, inversely proportional to the distance. To go from a proportionality to an equality, we have that term K, and that it will have a value. Q1 and Q2 is the amount of charge on each of the two objects. Q1 is the charge on object 1, Q2 is the charge on object 2, and R is the distance between the two objects. And it isn't just inversely proportional to the distance, it's actually inversely proportional to that distance squared. So this is a better answer, or a better understanding of the quantitative relationship between the variables. Okay, so instead quickly, F equals K, Q1, Q2 over R squared. All right. Those charges, Q1 and Q2, are measured in terms of Coulomb. So that's a new unit, the Coulomb. It's given, it's denoted by the letter C. And we'll talk about that in just a second, a bit more. The proportionality constant K is basically equal to 9 times 10 to the 9 Newton meter squared per Coulomb squared. If you want to be careful, which you probably do for homeworks, but within an exam, your answer, you'll be able to get close enough with 9 times 10 to the 9. You'll have the closest answer. But K is 8.988 times 10 to the 9 Newton meter squared per Coulomb squared. All right, a coulomb is actually a fairly large amount of charge. The charge produced by, say, rubbing a plastic ruler with a cloth, like we did in the last video, are typically around a microcoulomb. So that a micro is 10 to the minus 6, so 1 microcoulomb is 10 to the minus 6 coulombs. If you're not familiar with your SI units, go back. That was covered back in chapter 1 or 2 of the textbook. So go back and refresh yourself on units and how to convert between, say, microcoulombs and coulombs. That's a useful skill to have for this chapter. Okay, the smallest charge that we can find in nature is the charge on one electron. It's denoted as a nice italicized E. It's referred to as the elementary charge, and it equals 1.602 times 10 to the minus 19 coulomb. So a very small fraction of a coulomb. Hard to even grasp 10 to the minus 19, very small value. 10 to the minus 6 would be a millionth of a coulomb, so you're over 3 orders and 3 times smaller than that. Okay. Electric charge is quantized in units of the electron charge. So what does that mean? It means we can't subdivide electric charge smaller than 1.602 times 10 to the minus 19 coulombs. I can't divide that in half. All charge is a multiple of that 1.602 times 10 to the minus 19 coulombs. Protons have an equal charge but opposite sign. So an electron has a negative charge of that amount, a proton has a positive charge of that amount, 1.602 times 10 to the minus 19 coulombs. Okay. So if we come back now to our equation for Coulomb's law, F equals K Q1 Q2 over R squared, K is that proportionality constant, 8.988 times 10 to the 9, Newton meters squared per Coulomb squared. Q1 and Q2 are measures of the amount of charge on two charged objects, and those are measured in terms of coulombs, C. And R is the linear distance between the two charges, and that's the SI unit for distance is meters. So we measure that in meters. And now we're ready. We can solve problems now for the magnitude of force one charge exerts on another. Oh, and I mentioned before that I could say that it's the magnitude of force two charges exert on each other. Because if you think about it, the force that, say, charge 1 exerts on charge 2 is equal to the magnitude of this product. You take the two charges, divide by the distance between them, multiply by K, you get the force. But the force charge 2 exerts on charge 1 is going to be the exact same equation. It's going to be K, the amount of charge on object 1, the amount of charge on object 2, divided by R squared. So the magnitude of the force is the same regardless of whether we're looking at Q1 or Q2. This may be reminiscent of Physics 11:10 when we talked about, say, a truck hitting a car, which exerts the greater force on the other. When they hit, the forces are equal and opposite. It's the same idea here. You could have two charges, and one could be an electron, and one could be the charge of a lightning bolt, and the force between them is going to be, the magnitude of the force is going to be equal. So that's something else that's good to keep in mind. Okay. So that Coulomb's law gives us the magnitude of the charge. What about the direction? Force is a vector. It has both magnitude and direction, so we do have to consider that. The direction of force is along a line connecting the two charged objects. So let's look at that. So what we're going to do here is actually just an application of the concept that opposites attract and likes repel. So that's all we're doing, but we're going to add some fancy notation and so on. So if you have, for instance, two positively charged objects, charge 1 and charge 2, as shown here, they're both positive, so they're like charges, so they repel. So the force on charge 1 is going to be away from charge 2, so that's to the left, it repels. Or the force on charge 2 is going to be to the right, away from charge 1, so that repels. Our fancy notation is that we put two subscripts here. F12 is the force on charge 1 due to charge 2. F21 is the force on charge 2 due to charge 1. Okay, and if you remember, vectors can be shown with arrows, and so this is the vector representation of that force, And these two forces are equal in length, showing that their magnitudes are equal. They both can be obtained from that Coulomb's law equation, but their directions are opposite in this case. Okay, if I had two negative charged objects, again, they are like charges, so they repel, and we have the exact same geometry that we went through for two positive charges. If we have both a positive and negative charge, opposites attract. So the force on particle 1 due to particle 2 would be towards particle 2, so it's to the right. The force on particle 2 due to particle 1 is towards particle 1, so it is to the left. All right, I'm going to give you a little flash forward. If we had to add up these forces, for instance, they're all in a line, so if you go back and consider how to add forces, if they're on a line, they can be added or subtracted. So we'd have to choose a positive direction. Let's say positive was to the right, and then as we added these up, this would be a positive value for the force because it's in the positive direction to the right, and this would be a negative value for the magnitude of the value of the force because it would be to the left, and left is the negative direction. All right, if you want, pause for a second, think this through. It's important that we can draw these sorts of forces for different charges. So if it helps, pause for a second, and then when you're ready, let's move on. All right, one little detail to clean up, and that is that we can rewrite Coulomb's law in terms of the permittivity of free space. That's epsilon 0 here. So epsilon 0 is 1 over 4 pi k, or k is 1 over 4 pi epsilon 0. So this is just rewriting Coulomb's law in terms of the permittivity of free space. We'll see this epsilon 0 term again when we talk about capacitors. You may have seen it in a high school course, so I wanted to have it here for completeness, but it's much more convenient to solve Coulomb's law just in terms of k, so that will be the approach I will generally take. Always, actually. That's the approach I will take. Okay, so let's try an example. Let me read through this problem. So we're going to try to find the electric force on an electron by a proton. So determine the magnitude and direction of the electric force on the electron of a hydrogen atom exerted by the single proton in that atom. So Q2 we're going to make be the hydrogen atom, and it has a charge of plus E, because we just said the charge on an electron is E with negative charge. Charge on a proton is an equal magnitude, but it's positive charge. So that's what we mean by that. Plus E gives us the amount of charge for a proton. Assume the average distance between the electron and proton is as given here, 0.53 times 10 to the minus 10 meters. All right, so how can we figure out the force? F equals K, Q1, Q2 over R squared. We can bring forward Coulomb's law. So that's here. And I also drew a picture. It's always nice to have a picture. So there's our electron orbiting our proton. So we have a positive charge and a negative charge. We've arbitrarily chosen to make Q1 be the electron and Q2 be the proton. The force, and we want the magnitude and direction of the force on the electron. So we're going to figure out magnitude and direction of the force on the electron. I can just draw a picture here. They're opposite charges, so they attract. So as drawn in this orientation, the force is to the left. All right, let's figure out the magnitude. It's K, Q1, Q2 over R squared. K is this constant. I usually do 8.988 times 10 to the 9, but I'm going to be short on space, and I know that, so I wrote it as 9 times 10 to the 9. The charge on an electron and the charge on the proton is 1.602 times 10 to the minus 19 coulombs, and again, I've truncated a little bit for space needs. Okay, so now I can plug values in, and I had R, I didn't write it again, it's right up here, 0.53 times 10 to the minus 10. So I can plug in these values. There's F equals K. That's the value of K, 9 times 10 to the 9, Newton meter squared per coulomb squared. Q1 and Q2 are equal. So the charge on a proton equals the charge on an electron. And then the distance between them is given by that 0.53 times 10 to the minus 10 meters. So we make sure we square that. We multiply that through and we get the force. Now, some of you may be concerned. You might be saying, why isn't one of these positive and one of these negative? One is positive charge, one is negative charge. We don't worry about sign when we figure out the magnitude of Coulomb's law, and it wouldn't mean anything, because in order to figure out a direction, we have to look at the actual geometry of the charged particles. So we only put in the magnitude of the amount of charge when we put in Q1 and Q2. Okay. So we run that through a calculator and we get about 8.2 times 10 to the minus 8 newtons. It's not very hard to see that the units cancel. The meter squared here cancel with meter squared here. Per coulomb squared here cancel with those 2 coulombs. So we're left with newtons. I almost always do a units check when I do a problem because it's one of the fastest ways for me to realize I've made a mistake. Okay. So that gives us the magnitude, and so that is the magnitude of the electric force on the electron of the atom exerted by the proton. It also happens to be the force on the proton exerted by the electron, but because the K, Q1, Q2, and R wouldn't change. So that's the magnitude of the force each exerts on the other. The other thing we're asked to get is the direction of the force. So I'll clean things up a bit. Okay, and there's our picture again. And they're opposite charges, so they attract. So the direction of the force on the electron here, it's to the left in this image, but the electron's in a cloud going around the proton, so orbiting the proton. So it's better to say the force of the electron is just towards the proton, which is what I did. Okay, direction of force toward the proton, and we're done. A fairly simple example. It can look a bit messy because we often have a lot of exponents in these problems. Be careful to square your distance term. That's a common mistake. What else can happen? Make sure you put coulombs values in for Q1 and Q2, because by default, K has units of coulombs. So if you're given microcoulombs or something like that, you need to convert to coulombs so that your units cancel and you get a force in newtons with the right order of magnitude. All right, moving on. All right, so that's a nice quantitative problem. We can also ask conceptual questions with Coulomb's law. It lends itself well to conceptual questions. And just as a little flashback for those who remember their universal law of gravitation, that force was G, m1, m2 over r squared. The force that one mass exerts on another mass, you can see an absolute parallel with the form of this equation. So let me say it again. The force one mass exerts on another is G, that universal gravitational constant, m1, m2 over r squared. So if you mastered those sort of conceptual questions for universal gravitation, this should be this should be very straightforward. But if you didn't, now's a good time not just to master doing them for Coulomb's law, but you can apply your abilities back to universal gravitation. Okay, so let's try a conceptual question. A charged object experiences a force due to a second charged object. If you double the charge in one object and don't change the charge on the second object or the distance between them, what happens to the force? So pause the tape, think about it a bit, come back when you're ready. Okay, so what happens? Everything stays the same except you're doubling the charge in one object. So Q1, say, becomes twice Q1. So if we double that charge there, it's in the numerator, it's directly proportional to force, so it will double the force. So our answer there would be A. Okay, if that doesn't make sense, ask me in lecture or come to my office hours. All right, let's try another one. This was actually the opening chapter question. I've reworded it to match my last conceptual question, but it's the same content. And so I'll read it here. A charged object experiences a force due to a second charged object. If you double the distance between the charges and don't change the magnitude of the charges, what happens to the force? So again, this was the opening chapter question. And I used my charged object. I had the little frogs, and I had them a certain distance apart. And I said, we double the distance, what happens to the force? And at that point, I just said, does it increase or decrease? And hopefully you realize if the charges are farther apart, then there would be a drop. So that would limit you to two that would narrow the answers down to 2. Now you've got a 50-50 chance. So what happens quantitatively? If you double the distance, r becomes 2r, but that r value is squared. So the effect of having a 2r is to get a 4 in the denominator here. So the force decreases by a quarter, because your 2 squared becomes a 4 here in the denominator. Okay, again, if that doesn't make sense, ask in class and we can go over it there as well. All right, moving on. All right, so at this point, from this material, we can figure out the force on one charged object due to a second charged object. But let's say there was a third, oh, I have a third frog. Let's say you had a third or a fourth object, and you wanted to figure out the net force on one of those. So that's what we're going to figure out in this section. So the electric force between particles at rest, which are static forces, static charges, is a vector. When several forces act on an object, say force 1, force 2, force 3, all act on one, say, charged particle, the net force is equal to the sum of all the forces. So F net equals F1 plus F2 plus F3, but these are vectors. For this material, we're just going to focus on charges arranged on a line. So in that case, you can simply add or subtract the magnitudes of the vectors. You still have to think about it. It's still, takes some thought, but it's much easier. I don't want the focus of this chapter to be geometry. I want the focus of this chapter to be thinking about charged particles. So I have simplified your life a little bit there, but if you want to do some harder problems, they're in the textbook. There are answers in the back of the textbook. There's also a problem solved in the notes for this chapter, in the PowerPoint notes that I am not including here, but you can look through them online. But I'm not doing a lecture on them. Okay. So let's take an example. Let's say you had 3 charges arranged in a line as shown here, Q1, Q2, and Q3, and you want to find the net force on Q3 due to Q1 and Q2. How would you go about doing that? Well, I just said you add up the forces from each of the other. You add up all the forces acting on the object. So the net force on 3 is going to equal the force on 3 due to particle 1, and that's a vector, plus the force on 3 due to particle 2. So I would now go off and I would find the magnitudes of each of those forces. So I would use Coulomb's law and do F equals K, in this case Q3, Q1, over the distance between 3 and 1 squared. And I'd figure out the force on 3 due to 2. I'd do F equals K, Q3, Q2, over the distance between 3 and 2 squared. So I get those magnitudes, and then that would be step 1. And then I'd have to figure out how to combine those as 2 vectors. And so to do that, I have to look at the signs on the charges. So here, find the direction by looking at the signs. Opposites attract, likes repel. So I'm looking for the net force on 3. The force on 3 due to 1, they are likes, so they repel. So the force on 3 due to 1 is going to be away from 1 or to the right. If I make to the right be the positive direction, that'll be a positive vector. And then I need the force on 3 due to 2. They are like charges, they attract. So the force on 3 due to 2 is going to be towards particle 2, which is to the left. That's my negative direction, so that's going to be a negative vector. So because they're in a line, I can just add and subtract these values. And here we are giving a visual again of charge 3. The force on 3 due to 1 is to the right. The force on 3 due to 2 is to the left. And then I can add up those magnitudes. The force on 3 due to 1 is in the positive direction. That'll be a positive value. Force on 3 due to 2 is in the negative direction. That'll be a negative value. So I take the positive value of the force on 3 due to 1, and the negative value of the force on 3 due to 2, because that was to the left, and that will give me the net force on 3. So I'm going to stop there, and we just have a little bit more work to finish up in chapter 16. We'll be done. So when you're ready, come back, and until then, well, I'll see you then.